In this lesson, we're going to talk about the area and perimeter of similar figures. And what we know here, first of all, from prior lessons, we've talked about the Greek letter rho. Looks like an italicized P stands for perimeter. So whenever we see that from here on out, you're going to see the Greek letter rho, and you're going to read that as perimeter. The ratio of the perimeters of two similar polygons is equal to the ratio of the corresponding sides. So if we have these two triangles here similar to each other, ABC is similar to XYZ, by the definition, we know the corresponding angles are equal. So angle A would be equal to angle X, and angle B would equal angle Y. And since C here corresponds to Z, angle C and Z are equal. And also the corresponding sides are proportional, which would mean that I could write the proportion of AB over XY, since they correspond, would be equal to BC over YZ, and would also be equal to AC over XZ. So from the definition of similar triangles, we know this extended proportion right here has got to be true. And that's just saying that if they're similar, the ratio of the corresponding sides are equal, or they're proportional. Well, with this theorem, it adds one layer to that, and it just says, well, you have similar figures, the sides are proportional also with the perimeter. So the ratio of the perimeters of ABC to XYZ is equal to the ratio of corresponding sides. This right here we're going to talk about on the next slide basically could be a test question, probably will be, and that question is asking what is the ratio of the perimeters of triangle ABC to X, Y, Z. Finding the ratio of the perimeters. Okay, so here's the question I was just talking about a moment ago. To find that ratio, you find two corresponding sides that have numbers on them. So AC corresponds here to XZ. So the ratio of the corresponding sides would be 8 to 6. The order is important because it has ABC on top, so I need a side of ABC on top, XYZ on the bottom. So 8 over 6 is the ratio of the sides, which is the same as the ratio of the perimeters, according to the theorem that we just talked about. And we always want to put it in simplest form, so the ratio of the perimeters would be 4 to 3. The ratio of the sides is also 4 to 3. And also, we talked about in the prior lesson that the ratio of the altitudes is also equal to the ratio of the sides. So it would also be 4 to 3. That being said, how could we use that? If this is a right triangle, I'm going to make it that, and this side is 6 and this side is 8, this would actually be a relative to root off the 3, 4, 5 Pythagorean triple that we see often. It's a multiple of 2. It's a 6, 8, 10. I could use Pythagorean theorem to find that if I didn't know it. And with that being said, I know that the perimeter of this triangle would be, well, 6 plus 8 is 14, plus 10 more. The perimeter is 24 units, inches, feet, whatever they are. We don't have them labeled there. So how could I use this ratio of perimeters? Well, if I know this perimeter is 24, and the question was, well, what's the perimeter of this triangle? Well, I don't need to know all the side lengths. Since I have this ratio of perimeters is 4 over 3, and that's comparing ABC to XYZ. Well, the perimeter of ABC, the actual perimeter is 24, so in my proportion, I would put 24 on top. Compared to the perimeter of XYZ, well, that I don't know, so we'll call that rho. To solve this, then, we just simply take the product of the means equal the product of the extremes. So we know that 4 times rho is equal to 3 times 24, which is 72. And once in a while, this marker just puts some random lines on there, so excuse that. That should not be there. I divide each side here by 4, and the perimeter of this small figure or small triangle is 18 units. Kind of interesting. We just found the perimeter of this triangle, and we only knew one side length. We know all the sides are going to add up to that total of 18, and we knew that because of this ratio of perimeters. Now, likewise, you could find a side length too. We've done this in the past. If I wanted this side length, let's call this B. Well, to find that, the ratio of the sides is the same as the ratio of the perimeter. So I'd start with that same ratio of 4 over 3 is equal to, well, 6 corresponds to the B over there. So 6 over B. And the product of the means equals the product of the extremes. So 4B is equal to 3 times 6, which is 18. And when we divide by 4 on each side, my B value is equal to 4.5. So basically what this shows is you're just using that ratio. You're just using that ratio of sides or ratio of perimeters the same way. You can use it to find a perimeter. You can use it to find an actual side length. On to our next slide here. This particular one's talking about the Greek letter alpha, and alpha for us means area. So whenever we see this Greek letter alpha, we read that as area. And the theorem here talks about the ratio of the areas of two similar polygons is equal to the square of the ratio of corresponding sides. So the ratio of the perimeters was equal to the ratio of the corresponding sides, but here it says I have to square the ratio of corresponding sides to get the ratio of the areas. So in short, once again, this is a question, if you will. This is asking what is the ratio of the areas of ABC to XYZ? Well, what's it equal to? It's equal to the ratio of the corresponding sides squared. Corresponding sides of AB over XY, and we square that, and you could take any of the corresponding sides, BC over YZ squared, or AC over XZ squared. So any of the corresponding sides, the ratio squared would give you the ratio for your areas. In this next example, we're going to find the ratio of the areas because that's what the question's asking here. It says, what's the ratio of the areas of ABC to XYZ? Well, we already know from the prior example, same triangles we have here, the ratio of the sides was 4 to 3. And the theorem that we just had says we take the ratio of the sides and we square it. Well, when we square 4 over 3, you're going to get 16 over 9. Once again, that doesn't tell me the area of anything. It just simply gives me a tool I can use to help me find area. So let's go back to this guy here. If this is a right triangle, we know to find the area of a triangle, we take half the base times the height. Well, since this is a right angle, this 6 could represent your base. The 8 could represent our height. And we plug into the formula here for area. And 6 times 8 is 48, so the area ends up being, coincidentally enough, the same number that we had for perimeter. The area would obviously be, though, in square units, so the area is 24 square units. Well, if I wanted to know what the area of XYZ was, we would be able to find it, although I don't know a base and a height, by using this ratio of areas. Since the ratio of the areas is 16 to 9, I set this up in a similar fashion as I have any other proportion. So 6 over 9 is equal to, and that compares ABC to XYZ. So on top I need the actual area of ABC, which right here is 24. So we're going to put 24 over the area that I don't know, which is XYZ. We're just going to call that A. 16 times A, when I take the product of the means and set it equal to the product of the extremes, is going to be equal to 9 times 24. And when we take 9 times 24, we are going to get 216. All right, we divide each side then by 16. And when we take 216 and divide it by 16, we're going to get an answer here for this area. is 13.5. If you remember from the previous slide, we found this length here of xy using the ratio of sides. We got that this was 4.5. And interestingly enough, this being a right triangle, it would have to be if it was similar to the other one, we could use the area formula. And if I took and multiplied half the base of 4.5 times the height of 6, my area would equal, lo and behold, you multiply that out and you're going to get 13.5. So kind of interesting, you could do it either way and still get the correct area. But the cool thing about using this ratio, 16/9, is we don't actually even know the side lengths of this. I didn't have to know any of the side lengths, other than I needed to know this ratio of areas, and I needed to know the area of the other one, and I could simply solve to find the area of my unknown triangle there, XYZ, was 13.5. All right, so ABC was similar to XYZ. On to our next slide. Well, if I'm asked to find M, well, M is a side. We've got to pull out the right tool for the job, and if I'm asked to find a side length, I need the ratio of sides. And if ABC is similar to XYZ, the ratio of the sides, I could write it as 5:8 or 8:5. Doesn't really matter. So let's say that we wrote it as 5:8, and that's comparing the small triangle to the large triangle. The side of the small triangle that I want, that I don't know, is M, over the corresponding side of 6. So we get product of the means equals the product of extremes. 8M is equal to 30. When I divide this guy by 8, the value of M is going to equal, it's going to go in there 3 times, and a remainder of 6. So we are looking at 3.75. And likewise, to find N, I could find that in a similar fashion. I've got my ratio of my sides is once again 5:8, so 5/8 would equal N of the small corresponds to 10 over here, so it's going to be N over 10. So when I do the product of the means, 8N equals the product of extremes, which is 50. Well, 8 is going to go into 50 6 times, and it's going to have a remainder of 2. So we're going to get this equal to 6 2/8, or 6.25. Okay, well, with that being said, I've got the next question here. So I've got this is 3.75 for M. I've got 6.25. We just found N. And now it's asking, what's the ratio of the perimeters of ABC to XYZ? Now, I wrote this ratio as 5/8 because honestly it didn't matter. The question wasn't specifically asking an order. But here it is. It wants ABC to XYZ. So I need to compare a side of ABC, which is the 8 compared to the 5. So the ratio of the sides is 8:5. And what we learned today is the ratio of the perimeters is the same thing. So the ratio of the perimeters is also going to be 8/5. And this question, asking for the ratio of the areas of ABC to XYZ, well, we learned in the second theorem today that we're going to take the ratio of the sides and we're going to square that. So the ratio of the perimeters would be 64/25. Now, I don't know that I'd really need to find the perimeter because I already know all the sides here. I could add the 3.75, the 6.25, and the 5. I can get my perimeter that pretty easy. But what about the area? We already know the area of this from a previous example. We know that the area of that's got to be 24. And so if the area of that's 24, the question is, could we find the area of this XYZ? And well, now that we have this ratio of 64 over 25, running out of room here a little bit, but we could set this up and say 64 over 25, ABC to XYZ is equal to 24 over my unknown area here, we're going to call A. So 64A is going to equal 25 times 24 is going to give me 600. So I multiplied that, we got 600, and then we divide each side by 64. And as I divide by 64, it's going to give me the area, which is probably not going to be a real friendly number here. So we divide 64, and we've got our answer of 9.375. Now, it didn't ask me that question. The only question that was asked was the ratio of the areas, which we found here, the ratio of the perimeters, which we found there, and then it asked me for these two side lengths, which we've already found. I guess that was a bonus package there, finding that. So as far as the lesson goes for today, that should cover it. Remember that if you have similar figures, the ratio of the sides, the altitudes, and the perimeters are all the same. And then the ratio of the areas is always found by taking the ratio of the sides and squaring it. And once you have those ratios, you should be able to set up proportions to find either side lengths, altitude lengths, perimeters, or an area.